Just to tell you a few words about me, I did my PhD a long time ago, 2002, with Corinne Charbonnel, who is a professor in University of Geneva, and some of the ones of the Exoplanet Gang of Geneva might know her, and Manuel Forestini, who died just after my PhD completion. And I did this on stellar evolution modeling, and in particular the transport processes that affect the stellar evolution modeling. And maybe I will tell you a bit more in between slides about this. And then I engaged in a postdoc in Brussels at Institute of Astronomy and Astrophysics of Université Libre de Bruxelles, where their specialty is nuclear astrophysics, so where I gained great knowledge of some things that I'm going to present to you today. And there I worked on Aluminium-26, which was about to be observed by the Integral telescope satellite by ESA. Integral is a gamma-ray satellite that was meant to do the first high resolution, meaning this looking as a very square histogram of spectroscopy, gamma-ray spectroscopy of radionuclides, which Aluminium-26 is. And then I moved to Paris and worked on 3D simulations of stars, and back to my place, to where I'm from actually, to Montpellier, to the great joy of my family. So today I'm here I have about 3 hours to talk to you about nucleosynthesis. So from the presentations I saw yesterday, you have very diverse backgrounds, and some of you might know much more than I do in, well, all of you or lots of you know much more than I do in chemistry. The last time I did chemistry was a long, long time ago. We are going to talk about nuclear physics a bit. And then I will try to answer or to give you some clues on how, when, and where nuclides are produced. So I use the word nuclides, which is the word that we use in nuclear astrophysics or in nucleosynthesis, meaning the basic name of atoms or bare atom without the electronic shells around. And let's start. We have 3 hours. Before I start, I have 2 apologies to make. First, I won't be here for the rest of the week, unfortunately. So if you have questions, don't hesitate to ask them just after the lectures. And you have my email, and don't hesitate to contact me if you want further material or whatever. And the second is that I'm a bit tired, so I hope my English won't be too blah, blah, blah. The big question, it's good that I do not have too many astronomy pictures. The big question is, where do we, so as we, I think, and I think that here everyone thinks the same, living things, so not only we, but also plants, bacteria, and whatever, come from? So that's the big question that we have been as human beings asking and wondering about forever, I think. And another way to put this question into perspective is the way I'm going to address it, is where do the elements that constitute, that make living things come from? And so that's what nucleosynthesis is about. So nucleosynthesis is about nuclei that you synthesize, so know how you synthesize the nuclei. So most of you do, lots of you do chemistry, some of you work on biology, and in all these cases you work more with molecules than with atoms. But these molecules are made of atoms, and nucleosynthesis is about finding out how, when, and where these atoms are synthesized. And that's what we are going to address here. So it's a broad topic that spans from nuclear physics to galactic chemical evolution. And I will try to browse some panorama, hoping that it's not too low level or too high level. And I hope that it will give you some clues, or at least some reminders for those of you who already know about it. So the chemical elements, you know them all. They were organized in the 19th century by Mendeleev and other people at the same time, as always. Not only one super idea in a super researcher, but several people having the same ideas and converging into something. And so this periodic table of elements, there are nowadays 103 elements, and they are it's here presented in its classical chemical form with different families of elements, and the elements were classified by Mendeleev at that time. They had only 60-something elements at that time, and they knew the mass of the element. And they started. He proposed to organize them as with gathering their properties, chemical and physical properties, and the power of his finding, and that's why we still associate his name with this table, is that he saw a predictive power in this classification, and foreseen that some elements could be discovered that were in the family of hydrogen, for instance, or carbon or others. And so from these elements, we know that the living elements, living matter, is made of some of these elements, and all of this you know much better than I do. And we have, among the chemical known elements, there are 25 which are essential to life, and six major elements in living organisms, which are the CHN or the SNOPs things, and it's 98% of the human or of a human body, so it's a lot. And so we see that we have lots of oxygen, lots of carbon, and a bit of hydrogen, and the other things are a bit tracy, but as some of you know much better than me, they are very important to life. For instance, phosphorus, which is only 1%, is very meaningful because it's an atom that enters everything which is energy transfer in the cells, and so it's something that we want to look at. So the idea is that we have this table of chemical elements, and we have these elements that we find in living things, and we want to know where do they come from. So before we start on where do they come from, I think it's good to have a small introductory crash course on nuclear processes. And so just before I start on it, what I just would like to know, because there are physicists among you, but not that many. So who has some background on nuclear physics, nuclear reaction rates, thermonuclear reactions? Okay, so not that many. Okay, so for those of you who know about it and do not hesitate to, well, I was to say do not hesitate to interrupt me, but no, do not interrupt me. But just keep corrections or supplementary things in mind for when we have questions. So I'm going to talk about what's a nuclear reaction, how it works, because it will be fundamental to explain you how these atoms are synthesized. So here what you see is a different way to organize elements compared to the periodic table. This is the nuclide chart. And this nuclide chart is a two-dimensional representation of nuclear and radioactive properties of all of all atoms, and so it's a chart that where you have in the abscissa you have the number of neutrons n, and the ordinates you have the number of protons z. So when you are here at the bottom you have hydrogen, and up there you have the latest, the heaviest elements. A color coding that is interesting in this chart is that everything that is black here, the black dots, are stable atoms, and so this is called the valley of stability. And you may see that at some point, for the very heavy ones, you have no stable elements anymore, And what does it mean that they are not stable? It means that they will decay radioactively at some point to go back to stable ones. So everything that is on each edges of the valley of stability has a half-life that might be very long, but not always. And in the end, they can decay to the black ones. Each line represents isotopes of the same atom. And you see also that the heavier the atom, the more you have new isotopes, expected for the very big ones here, which are quite difficult to synthesize. Most of these very heavy ones are synthesized in human laboratories. They have not been observed in the universe. And they have half-life times of very short ones. So we don't know yet all these isotopes. So to understand the way you populate this chart and the way you go from one isotope to another, or from one line to another line, you need to have some basics in the physics that are there. So there are several ways to populate this. Some elements are built from neutron capture, which are everything that is blue here, so the neutron-rich elements. Some elements are proton-rich, everything that is reddish or magenta-ish here. And then you have these very unstable elements up there. And there are several pathways to explain the formation of all these elements. So the first pathway is the decay, radioactive decay. And it involves some of the fundamental interactions in physics, which I recall here. So we have the strong force, which is the one that keeps nuclei together. And it's a force that appears in nuclear fission and fusion. And it determines the quark structure of the proton and neutron. Then you have the electromagnetic force, which works with... so this is the particle that is the driver of the force. So you have the gluons for the strong force, the photon for the electromagnetic force, where you have the interaction of the nucleus and the electrons, because it's for charged particles. Then you have the weak force, and this weak force is very interesting. It's the one that appears in beta radioactivity. I will come to it just after. Next slide. And it's the force that is allowing a proton and a neutron to convert into a proton, which is not really a conversion, but in this way, what you have to know is that neutron and protons are made of the same quarks, which are the even more fundamental particles. And quarks oscillate in nature. They can change nature, change flavor and color. And the thing is that in order to build up a proton, you have to exchange a boson, W, most of them, or Z boson. And this will allow you from a neutron to produce a proton and emit an antineutrino and an electron. And then you have, of course, gravitation, which is the force with the largest scale of action, and which explains most of the architecture of our universe. And the particle for gravitation is not yet found. So the nuclear processes that we have in this chart of nuclei. So we have the stable nuclei, and then outside the valley we have spontaneous decay, radioactive decay, and there are various types of radioactive decay. There's the alpha decay, which is a strong interaction, meaning that your nuclei will split, and they won't split in whatever manner. They will just emit an alpha particle. So an alpha particle is a bare nucleus of helium. So this is the strong decay. It's alpha decay. Then you have the weak interaction, which is the beta decay, which is the normal radioactive reactions that you know of. In this process, there's a weak interaction because you have a conversion of a neutron into a proton, and an election. So, as I just showed you, when this appears, this happens due to the reorganization of the quarks within the particles. You will emit an antineutrino or a neutrino, depending on if it's beta plus or beta minus, and an electron. And so this is the weak interaction. And there's another one, which is the gamma decay. This will happen a bit like when you have an emission of, in a spectrum, where you look at emission lines in a spectrum, which correspond to a change of energy in the electronic shells. Here, it's you have a nucleus that is in an excited energy level, and that will decay, but the entire nuclei, it's not an electron changing orbit, it's the nuclei that decays, and it will emit a photon, and this is electromagnetic interaction. So now we see that in the chart that we had before, which is here again, we can read this chart in another way. So here you have the line with equal number of protons and neutrons. And you see that beta minus decay will may have the nuclei go to the value of stability with decreasing neutron number. Beta plus decay will lead you to the value of stability with decreasing proton number. And alpha decay, so this one of emitting particles, is the radioactivity that involves the very heavy elements that go down, move down in neutron and proton numbers. And so to move from one element to another, if you go up, you capture a proton. If you go left, the other left. If you go right, you capture a neutron. And if you follow the diagonal here, you capture an alpha particle. So now that we have an idea of these elements, in addition to radioactivity that helps you populate this chart, for the stable elements, what synthesized them is thermonuclear reactions. So the elements can be classified according to their binding energy. So the binding energy is the energy it's a negative energy, because it's not an energy that the atom possesses, but it's the one that the atom that you need to bring to the atom to cut it, to break it. And so it's made of the number, the mass default, so you recognize all the equation of Einstein. So it's the number of neutrons times the mass of the neutron, plus the number of protons times the mass of the proton, plus the mass of the entire nucleus. And this means that in a nucleus, it's not a nucleus is its mass and energy, because of this relation, is not only the sum of the mass or energy of each of the constituents, but it's something more. This was found out by Einstein and gave up this idea of the mass defect. If you want to classify these binding energies depending on the mass number, which is the sum of protons and neutrons inside the nucleus, you have this, which is an absolute value because the binding energy is negative normally. And it's given here in energies, which is done a lot in astrophysics. So the mass of an electron, because of the equivalence between mass and energy, it can be expressed in electron volts, so in an energetic unit. So it's 0.511 mega electron volt. And you have here the binding energies of the nuclei. So you can compare them. It goes up to 8.8 for the iron. And what you see is that this curve is not whatever. There's a pattern in this curve. You have light elements, hydrogen here, with a low binding energy. And this will help make it quickly in the history of universe. Then you have helium, which has a very high binding energy, and we will come to it later. And then you have just increasing binding energies up to the iron group. In these elements, you have kind of you have an equilibrium, a kind of maximum of bindingness. So these elements are mostly tightly bound, and the other ones are not that tightly bound because then you have they are too heavy, and it's difficult for them to be stable. And so you have a curve that divides into two parts. One part which is with increasing binding energy, and another one which is with decreasing binding energy. In terms of thermonuclear reactions, it means that to synthesize elements from hydrogen to iron, you will have to pile up small elements, which is called fusion. And on the contrary, to build these ones, it will be built, this part of the elements is built backwards, meaning that you build from seeds, you increase the number of neutrons in these elements, but then they are not tightly bound and very easily destroyed, in particular with radioactivity, and you will have nuclear fission. Okay? And in both cases, you will emit energy, and that's what we are going to look at, and how we traced them, actually. There will be a few slides with some equations, but do not worry, there are not that many, and I think I decided to show them because I think it's a bit important for you to have a good picture on how nucleosynthesis works, to have a good understanding. So first of all, because I know we all come from different communities and notations can be something quite tricky as vocabulary, not using the same words to talk about the same things. It even happens within astrophysics, classical astrophysics. So a nuclear reaction can be noted as a chemical reaction, this way. And so this is the target nucleus, this is the projectiles, this is the daughter nucleus, and these are the additional particles that are emitted in the process. And it can also be noted this way, so XA yielding Y and B. Okay? And this notation you will see in other slides. So when you have a thermonuclear reaction, you must comply to the laws of physics, and in particular you will have conservation of charge and baryon numbers. And so charge is noted Z, so the sum of the charge of the two elements involved in the nuclear reaction is the same before and after the reaction, and it's the same for the baryon numbers. And you also have conservation of energy. And here you have the energy, a bit like we talked about before. You have the energy of each of the elements in the nuclear reaction. And you also have these additional energies, which are the energies in the center of mass of kinetic energy, because as you have moving particles, you have to find a framework within which you can describe the movements. And so this is the center of mass framework that we use in nuclear physics. The energy that is produced by a nuclear reaction, be it fission or fusion, is called the Q value. And the Q value is the difference between the masses of the mass energy of the particles that interact in first, and with the mass energies of the particles that are formed, that are synthesized. And you see that this Q value, as you have a sum here, with something and something subtracted, might be positive or negative. So when the Q value is negative, this happens for nuclei that are heavier than iron, so the ones here. It means that instead of producing energy, you have a negative production, so you consume energy. This is called endothermic reactions. And this explains why you cannot fuse elements, because each time you want to combine them, instead of making energy, you consume energy. So in this part, for this nuclei, you will only have fission. On the other part here, which is the one that we will be more interested in, because this is the way we build up these elements, you have exothermic reactions, meaning that when you have a thermonuclear reaction between two elements that have a mass comprised between hydrogen and iron, it will release energy. And this is very important for stellar physics and in general, because this is why, and I will go back to it later, this is how stars make energies and radiate. Now that we have these clues, the thing is that what we want to know is how elements are built, and to build an element you need to have both of them, so the projectile and the target, to collide at some point. Okay, so we can do this in colliders, but we can also look theoretically how it works. When you collide these elements in a reaction that involves a particle A and a target nucleus X, you will produce an amount of energy, and this amount of energy is equal to the amount of energy that you liberate, the nuclear reaction rate, meaning the number of reactions per second and per unit volume that happens, divided, because this is a specific energy production rate, by the density of the medium. Okay? As you will see, I will drop the product of the nuclear reaction, because normally if you have two particles interacting, a proton and a carbon-12, for instance, you can only make one. The outcome is just one specific nuclei. So we normally drop the Y. That's why it's here. And so the reaction rate, it depends on the number density, of course, of particles A and X, their relative velocity, and the cross-section of the reaction, which is called sigma. And this is a nuclear reaction rate, and this is what we try to understand and characterize, and what explains the synthesis of all the elements in the Mendeleev table. And so the reaction rate is the number of reactions per nucleus, per target nucleus per unit time, divided by the number of incident particles, so particles A, per surface unit and time unit. And this reaction rate is often referred to as the mean value of the velocity, so the sigma v here, times the Avogadro number. And so this is what we, in nuclear astrophysics, call a nuclear reaction rate. So what we want to do is how this behaves in terms of energies, temperatures, and nuclei. Why do we care about this? Because this will tell us how we can build up the different elements. So in a classical framework, when you want to do a nuclear reaction to occur, the energy of the projectile must exceed the Coulomb barrier, which is due to the electromagnetic force, in order for the projectile to fall into the well of the strong interaction within the target nucleus in order to make a new nucleus. And so this was known in early 20th century, but there was a problem, and the problem was that for a proton-proton reaction, which you could say it should be the easiest one because you just have two protons that need to be put together, we realized that due to the high Coulomb barrier of the protons, it would require temperatures that are above billion Kelvin, and billion Kelvin is very difficult to attain. And so if this would be the only way to synthesize elements, we won't have any elements, complex elements in the universe, because there are very few environments in the universe that attain such high temperatures. So there's something else, and this something else was understood quite rapidly with quantum mechanics. And this something else was first hypothesized by Gamow in 1928. And Gamow said that according to quantum mechanics and to the wave form of the atoms, of the particles, there's a non-null probability that the projectile actually tunnels through the Coulomb barrier to interact with the nucleus. And so it will tunnel, make a composite nucleus, and then the daughter nuclei of the nuclear reaction. And so it's kind of the magics of nature that to build everything that we are here, we need to have these very, very tiny probabilities to happen. And this is possible only because we have so many particles in the universe and some places where there are very high temperatures that give enough energy for the tunneling to happen. So the energy that maximizes the probability for this interaction, for the tunnel effect, is called the Gamow window. And the Gamow window, I will show you here in this plot that shows you energy, probability of interaction as a function of energy. And you see that the Gamow window is the interaction between the distribution of particles, energy distribution of normal matter particles, which is the Maxwell-Boltzmann distribution, which goes as energy divided by kinetic energy, thermal energy, kT. And here the Coulomb barrier, which has this form. And the place where both tails of distributions interact is the energy that maximizes the probability of a nuclear reaction. And another way to show it here is just for carbon involving nuclear reactions, and we will come to it later. Do not worry if you don't understand this graph now. If you plot the density and temperature in this view graph, you can estimate, you can locate the places where the Gamow range is reached for proton capture on carbon-12, proton capture on carbon-13, alpha particle capture on carbon-12, and 2 carbon-12 nuclei interacting. And what we see is that it requires higher and higher energies for this to happen because the Coulomb barrier are higher and higher. And so this means that it cannot happen everywhere at once. And we can identify the locations, where these kind of nuclear reactions happen. So to finish and wrap up on thermonuclear reactions, I have the last thing to talk about, which is non-resonant and resonant reactions. So a nuclear reaction can be a non-resonant one, meaning that you have a target nucleus, a projectile, and the projectile will enter the Coulomb barrier directly and fit directly within the lower energy level of the target nucleus. So this is a direct capture, and it leads, when you want to plot the cross-section of the reaction in terms of energy, it leads to this kind of curve here. So, and which scales something like a square root of energy. And what is shown in this image is that you have several orders of magnitudes in energy, and that in nuclear physics laboratories, experiments, accelerators, you can directly measure this kind of reactions, but it's very difficult to go to the energies that are the ones that have the Gamow energy, and so there's a great work to do to extrapolate. So you need measurements, theoretical computations of quantum physics to extrapolate on the nuclear reaction rates that are actually meaningful for astrophysics. And then you see that in this curve, you also have this kind of spiky things, and these spikes are due to resonant nuclear reactions, and you will understand in a few minutes why I talk about this, even though it might seem very technical to you. It's a bit important because it's due to a resonance that we understand the formation of heavy elements. So these resonant reactions, they happen when the energy of the incident particle corresponds to a difference between two levels of energy in the target nucleus. So the probability is not that big. But then in the way it's schematized here, you have the projectile on the target, and it makes a compound nucleus, which is unstable. And this, you will have the gamma decay that I talked about before. You make this element. Normally the notation is, for instance, if it's carbon 12, it will be carbon 12 with a star, meaning that it's excited. And then it will decay to a final state, which is the compound nucleus. And so in this way, in this place, as you see, you have the spikes here, meaning that when you have a resonance, you have a magnification by several orders of magnitude of the probability of interaction between these two species, A and X. And so this, when you have a resonance, the non-resonant reaction rate is really orders of magnitude below. So resonances are very important because they can change completely the yield of your nuclear reactions. You may have nuclear reactions that in normal non-resonant conditions appears to be very, how would we say, not very efficient. But then if you have a resonance at a certain energy, the target nuclei and projectile nuclei at certain energies, you may amplify the reaction rate. You have understood that to build up the stable nuclei, we go through thermonuclear reactions. There are two ways to do it, fusion and fission. And in fusion reactions, we build these cross-sections that I talked about. These cross-sections depend on energy. They have a specific form, mathematical form that I didn't show. And what you might expect from what I told you about the tunnel effect and everything is that this nuclear reaction rate drops enormously when your Coulomb barrier increases, because it's very difficult to overcome the Coulomb barrier, and so the probability that you actually tunnel is very low. So the reaction rates, they are very different comparing to the Coulomb barrier, and so comparing to the initial mass of the nuclei. The other thing that is important is that the nuclear reactions, cross-sections, they depend very highly on temperature. And this is very important because this means that thermonuclear fusion reactions of hydrogen and carbon, for instance, they will occur at very different temperature. Why is it so? So this is related. To overcome the Coulomb barrier, you need more energy for the particle, and to have more energy, you need a hotter medium, normally. It also depends on density of the medium, but in a much less important way. So that's why normally it's overlooked, the density dependence, even though in proper thermonuclear fusion reaction computations, you include, of course, the dependence on density. And the thing is that as they occur at very different temperatures, these nuclear reactions do not occur at the same time. And this is very important because, as you will see later this morning, this explains stellar evolution, actually. Only these purely nuclear physics facts. Here you have some values of the types of nuclear fusion reactions. So proton-proton, proton capture on nitrogen-14, alpha particle capture on carbon-12, and an interaction between two nuclei of oxygen. And what you see here is that the dependence in temperature is the highest when you go to heavier elements. You see that it's to the power 182, depending on the temperature. And here you have the height of the Coulomb barrier that you have to overcome. Of course, for proton-proton, the Coulomb barrier you have to overcome is the mass of the electron. He is the one shielding. But if you have heavy nuclei, you have lots of electrons, and so you have to overcome a larger barrier. even though within stars, I talk about the electrons, but as you all know, when the gas is very hot, it becomes a plasma, and you all know very well about it. And so in the plasma, the electrons are not around the nuclei anymore. So that's what we have in stars. We have these plasmas. But the electrons are here around the electrons, and they contribute to the nuclear reactions through something that we call shielding. And so they also act as if they were around the nuclei, even though they are not around their proper nuclei anymore. So now back to these elements. So now if we go back to these elements, we have talked about basics of nuclear physics. So we know that the light elements up to iron, everything here is built by fusion, that everything here is built by fission, and that considering the different isotopes, they are built by beta decay or alpha decay. Okay? So now you know how they are organized, everything. So this is the origin, but now we want to know how and where. We know how it happens. We want to know when and where it happens now. And there's a color code in this periodic table, and we will come to it later for you will have the color code later. But it corresponds actually to when and where this happens. So to address these questions of where and where this happens, the first thing that we have to do is to measure the abundances of all these elements. And we can measure them in the Earth crust. We can measure them in whatever, actually, if we have a spectroscope. Spectroscopy, you can do it with all kinds of things. And to know the origin of elements, what we want to know is how these elements, now that we have identified them, how they distribute in the universe. And so it's a big task to know how they distribute in the universe as a whole. So as a starter, we will look at how they distribute in the sun. It's the first thing, or in the solar system. And then there will be an hypothesis to go from this to what we call the cosmic abundances. So the cosmic abundances, they refer to the chemical composition of the sun and solar neighborhood. And this chemical composition of the sun, it is determined through two ways: spectroscopy, so in situ spectroscopy or in situ analysis, chemical analysis of the chondrites, which you have here, and here you have a small cartoon of the proto-sun, proto-solar nebula. I think you all more or less all know about it. So I'm sorry, I'm very bad at names, so I don't remember, but I know that there's someone working, at least 2 or 3 people working on the jets and on looking at the elements that you can find in protoplanetary disks. So you might have remembered better than me who I'm talking about, and so you can go to them for more information. But here, what you have is a cartoon of what should have been the proto-sun here, surrounded by a disk of gas and dust, within which these chondrites were formed, and they've been preserved since then. Not completely preserved because they are since then been exposed to radiation of the sun and cosmic ray particles, attacks and things. So it's not that easy to say that what you measure on these chondrites is exactly what was there when the sun formed 4.6 billion years ago. But it's a good match. And the chondrites are very interesting because from them you can have isotopic abundances, which is not the case directly from the spectroscopy. And the spectroscopy is the one of the analysis of the photosphere of the sun. So the photosphere is the part that gives you, from which light escapes. And here you have a Fraunhofer spectrum of the sun from dating back to 1840. And you see here the Planck function. of energy distribution. And here you see the spectrum and the elements that have been identified. So each of these lines correspond to a transition into for atoms, energy levels. And you see that you have absorptions lines, which is the parts where you have less light coming. And so we do spectroscopy of the photosphere to determine most of the elements. Some of the elements are difficult to catch in the photosphere, and so we measure them like neon in the corona of the sun. But more or less, with both techniques, we are able to put up something that is called cosmic abundances. So we have for the sun, we do like this. For stars other than the sun, we will do chemical analysis mainly through exclusively, I would say, but not that much, but through spectroscopy or spectrophotometry of other stars, but also nebulae and external galaxies. And for the neighbor stars and the interstellar medium, we see that we have a similar abundance distribution than the solar system. It's a relative distribution, but there's a solar scaling to be applied, meaning that. So let me introduce, because here I have this notation for the first time, and I didn't specify. So if I go back, sorry, I do a small parenthesis, but it's for you to understand. If I go back here, this is a chemist or normal periodic table. An astrophysicist table would be hydrogen would be named X, helium would be named Y, and everything else is named Z. So X and X plus Y plus Z equals 1. So X, Y, and Z are mass fractions of the total mass of the baryonic matter. And X is the mass fraction of hydrogen, Y is the mass fraction of helium, and Z is what we call the mass fraction of metals. So for sure, all of these do not have chemical properties or physical properties of metals, but in astrophysics, that's how we call them. So Z is what we also call the metallicity, which is the amount of heavy elements. Okay? Why do we do this? You will see it in 2 slides. So we have variations of the amount of heavy elements compared to the amount of hydrogen in other stars. But we have something which is a relative distribution which is the same, which brings us to this assumption that the local abundances something is happening in the birds world. That the local abundances are referred to as cosmic abundances. So we moved from Earth-centric system of philosophical view of the universe, but not always, and sometimes it's still useful to bring everything back to us and to the sun. And so that's what we get for the sun. And what you would get with amounts that are different, but the relative abundances are like this. So here you have the relative abundances in a very strange scale that only astrophysicists use, which is we use a scaling of an amount of 1 million atoms of silicon. This is the 0 of the scale, and so it's here. And then you compare everything else to the amounts of atoms of silicon. And so you see that hydrogen is up there at 12 in log scale. So it's 6 orders of magnitudes more abundant than silicon. And you see a very specific pattern in these cosmic abundances, which is what we want to explain with what we call the nucleosynthesis, meaning why do we have so much hydrogen? Why do we have so few lithium, beryllium, and boron? Why do we have a peak here? This you know already. These are the more tightly bound nuclei, and so we have a nuclear statistic equilibrium that favors the accumulation of these elements because they are the end point of both thermonuclear fusion and fission. Okay, so you have an accumulation here. And you see you have other accumulations here around strontium and another one around lead, which are the end products, the mean end products of very heavy elements fission. When we compare the abundances of all these elements found in the solar photosphere compared to what is found in chondrites, it's very satisfactory. It's very nice to see that you have a beautiful fit of 1-to-1. You can forget about these ones. We don't forget about these ones because these, as you see, these are the ones that you are interested in exobiology, astrobiology, carbon, nitrogen, oxygen, hydrogen. They are all here. But for all the other ones, we have a very nice line. So the discrepancies between both are interpreted in terms of the evolution of the solar system and of the sun itself. So lithium is lower in the sun because it is destroyed in the sun by nuclear reactions, captures of protons on lithium-7, which is the most abundant. But even though it's the most abundant, look at here, the lithium is 10 orders of magnitude less abundant than hydrogen. And for the other ones, we see that they are more abundant in the solar photosphere, and it's because in the sun environment, these are volatiles, and so they were lost from meteorites when the meteorites formed. And so that's how we explain the discrepancies. But they are very informative. Actually, these discrepancies are very informative of the physical conditions that reigned when the sun and the planetesimal and dust were formed in the early history of the solar system. So what we see is that in the end, in the sun we have this, and in the early days of the universe, and I will come to it just in a few seconds, we came from abundances that can be estimated through the study of the further oldest light in the universe, which is the one of the cosmic microwave background and models. We have 75% of hydrogen, 25% of helium, and no metals. So now you know what Z is. So nothing heavier. Actually, there are traces of heavier things, but they are really traces. And when we look at the solar system, meaning at something that was built 9.4, yeah, something like this, billion years after the beginning of the clock, after we stopped the clock, which is the model of the Big Bang, we have much more elements. Even though all these elements, they only constitute something that less than 2% of the matter. So it's very, very, very small. But it's a very small part that is very important, of utmost importance for us. So there's been something here, and the something between the early universe and now is stars. Stars have happened. Stars have lived and died. So stars, because there are biologists here, stars do not live and die, as you may know. They are not living things. But we always use these words as we use hydrogen burning instead of hydrogen fusion, even though there's no burning, it's actual thermonuclear fusion. So just to make clear, so what we call a life of a star is the part of the star, the part of its lifetime, when the energy is produced by nuclear reactions, okay? And what we call the death of a star is then either you do not have any star left anymore, or the star is not left anymore, is destroyed, or the star is maintained, but not by nuclear reactions. Something else maintains the star, and these are dead stars. Not Death Star, but dead stars. And so we are going to see now how we go from one to the other. So now I show you again this periodic table. You will see it again twice, or I guess. So I guess by the end of the morning, you will have it imprinted in your mind if you do not sleep. And so the colors correspond to the nucleosynthesis sites. So the origin of the elements, and let's start going into what I was meant to explain to you, but I think all the introductory part will help you understand what we are going to discuss now. They have different sources, and how we know this is that the abundances allow us to infer the physical conditions of the productions of the nuclei, because we know nuclear physics, and so we know that for the synthesis to happen, we need temperature, in particular temperature and density conditions that are specific. And so to this, we are able to trace the places where these physical conditions are met. And so there are not that many places. There's the Big Bang nucleosynthesis, and we will come to it. So this is what we call the primordial nucleosynthesis, or BBN, for Big Bang nucleosynthesis. This is responsible for the majority of baryonic matter, meaning hydrogen and helium, and a bit of lithium. Then you have stellar nucleosynthesis, which is everything which is here around, the green things, and the green things, let's say. And you also have explosive nucleosynthesis, where you have neutron captures and beta disintegration for the very heavy elements. And you see that you have different ways for a star to die. And as the star dies, you may have very energetic events. And these events will bring very heavy elements. So stars can explode. Different living stars or dead stars can explode, and they can also merge. And this is new science that is a very active field these days. And so you see that in the end, if we refer to what Carl Sagan say in his program, I don't know if it was radio or TV program, when he first said the word that we were stardust. It's actually true. We are mostly stardust, and a bit of even Big Bang-ish dust for the hydrogen. So all the elements that make everything we see here came from a star or from the early universe. So now in the following, I will just show you what are the reactions and what happens in these different sites. So the Big Bang theory is the current theory that we have to explain the evolution of universe. It's a theory that goes background, that allows us to go back in time. So the modern cosmology was founded in the early, first part of the 20th century, and it relies on two main principles. The first one is general relativity, that was proposed by Einstein in the early 1920 something, after the first, not 20, maybe 1913. The specific relativity was published in 1905, and then from this special relativity, out of which the equation of equivalence between matter and energy came out, he just dug more into this physical laws and came out with the general relativity. And what does general relativity tell us? It tells us that space and time are intertwined, as energy and matter are intertwined. They are related to each other, and both of them are related. So space and time and energy matter are related, and this makes general relativity a generalization of the theory of gravitation. So you have a Newtonian gravitation is embedded within the general relativity, and then as you go to high energy, you come up, and so to the universe as a whole, you come up with this kind of relations. The other principle that we have for the Big Bang theory is the cosmological principle, stating that the distribution of matter energy in the universe is homogeneous and isotropic, and leading to something which is this hypothesis, saying that matter is uniformly distributed at large scales. I think it's SDSS survey, or I don't remember which survey. So it's a deep survey, what we call deep survey. So we look at the sky with very long poses, and we try to make a cartography of the matter, galaxy, clusters of galaxies, in very deep observations. And what you don't see is that it's more or less uniform. You have fluctuations, and there are some voids, some cosmic voids, they exist, but there are not that many. And the cosmological principle seems to be more or less okay. So considering both of these hypotheses, and in particular, if you apply the theory of gravitation as described by general relativity to a universe that obeys the cosmological principle, so that is homogeneous and isotropic distribution of matter and energy, this yields to a non-static geometry for space-time. And this non-static geometry for space-time tells us that there's a scaling factor that affects distances between fixed points, meaning that when you go back in time, all the points were closer together, and in a universe that was denser. And that's how you come out with the Big Bang theory. So nothing exploded at no moment, but it's just that if you look at the conditions of the universe nowadays and you apply this, you can just go back in time in your movie, and it means that at some point the universe was very small, very dense, and very hot. Okay? This theory is not the only theory, and it's important for you as young scientists. I think you are all convinced, but these are only theories that are right until they are proven to be wrong, as it has been the case for many theories. Sometimes they are not fully wrong, they are just wrong changing perspectives. And still work as Newtonian gravity still works for our nowadays life, everyday life. But still, the Big Bang theory is with some additions which are inflation times, which is a moment in the universe, in the very early universe, where the universe must have expanded very quickly in order to explain the structures and temperatures that we observe. It's the theory that is validated by most of observables, almost all observables. There are other alternative theories which imply chords and these strings, cosmic strings and things like this, but they are not today validated by as many observables as the Big Bang theory is. Okay? Within this Big Bang theory, the matter density determines the geometry of the universe, and it controls its time evolution. And important point also of this is that, of course, this allows us to check the temperature and matter density in the early universe. Last thing to say, the Big Bang theory is our best theory to understand how the universe evolved and where we come from, if we have the big question of where we come from, not as living things, but as an environment. It's the Big Bang theory, but yet this Big Bang theory has something which is, it's not a failure, but a weakness. Well, not a weakness, but yeah, more or less, is that it explains very well only 0.4% of our universe, which is baryonic matter. And all the rest is what we call dark matter or dark energy and dark energy, which are things we don't know what they are actually. And it's the work of particle physicists that to understand this. But just for you to, it's always quite amazing to know that we have a perfect theory to understand the matter as we know it, the baryonic matter. But this baryonic matter and what we know and what we are made of is a very tiny little, super tiny little bit of the entire universe. And most of the universe, which is dark energy, we do not understand how it works or what it is even. So it's still a very big question. So within this Big Bang theory, it was proposed in the early 20th century and then validated. And so this is what I was talking about. This theory is the one that we have adopted because it's validated. It made lots of predictions, and these predictions have been validated, and the last validation was in 2015, wasn't it? Yes, with the gravitational waves measurement events that we actually measured, and that were also a prediction of the general relativity and the Big Bang theory. So there are three observational confirmations of the model. The first one was made by Edwin Hubble in 1929, when at Mount Wilson Observatory, he was observing galaxies, distant galaxies, which were not actually known as to be distant galaxies, but they were distant structures. And looking at them, measuring with spectroscopy, measuring velocities, dispersion velocities, and he found out that the further objects were at greater velocities and that the universe was expanding, as was predicted by the Big Bang theory. So this was the first observational proof of Big Bang theory. Then came the second one, and we will come back to it just after, but let's go chronologically. In 1948, these three guys, so Alpher, Bethe, and Gamow. Donc I already talked about Gamow for the nuclear reactions. So these guys will show up in many other papers, fundamental papers. They came up with this letter to the editor, which I cropped here, but it's just one page. It's a very short paper. It's a bit like the Einstein's paper. It's 4 pages and it changes physics. And here it's 1 page and it changes our understanding of nuclear synthesis. And they proposed that various nuclear species must have originated not as a result of an equilibrium corresponding to a certain temperature and density, but rather as a consequence of continuous building up process arrested by a rapid expansion and cooling of the primordial matter. Okay, so they refer to this Big Bang theory where the universe is very dense and hot, and there's a moment where it evolves to less dense and cooler, it cools down. And they find that there's a tiny bit of window where you can build up the first elements, the lighter elements. And then the third, and so I should now add the 2015 measurement of gravitational wave signal, but the third historical observational confirmation to the Big Bang theory is the discovery of the cosmic microwave background, which has a temperature of 2.73 Kelvin, by Penzias and Wilson. They were using these telescopes, you know, the radio telescopes that are a bit like, I don't know, it doesn't look like a telescope at all. It looks like just tiny bits of I don't know how to say it actually in English. It's my... Sorry?
Antennas?
Yeah, no, there are not big antennas if you look at it. It's just like the things you use to put your clothes to dry, you know, your hanging strings. It's something like this. And actually they didn't believe their measurement. What they found is that they were doing observations and there was a signal they couldn't get rid of. And every measurement they did, there was always this signal pointing to these specific temperatures. Please comment. And they checked on birds' nests and everything. And finally, they came out with but maybe it's something related to the Big Bang. And it's actually the oldest light that we can measure. It's so this cosmic microwave background, for those of you who don't know, is the light that was emitted and that confirms the cosmological principle. So the universe is dense and hot. And as the universe is very dense at this moment, nuclei and photons are intertwined, meaning that the universe is fully opaque. Photons cannot escape matter. And at some point, because the universe is expanding and cooling, there's the decoupling between matter and light. And so the first light is emitted. This is also, by the way, our horizon. We will not be able to observe beyond this because there's no observable to us. Then this light emitted just kept on propagating, and we still observe it, and we see the cooling down of the universe. And now it's not that far away from the absolute zero, so it's 2.73. And when you trace the curve of energy as a function of wavelength, so the Planck radiation, it's a perfect black body. It's the best black body we have. We are not able to build black bodies that are as good as this one, and where the weight of the line weight is even larger, or of the order of the error bar that we have on the measurement. So it's a very beautiful physical experiment with this CMB. And so this CMB shows that the universe was dense and hot once. Everything shows that the universe was dense and hot once, and then came the Big Bang nucleosynthesis. So let's go to it. To show you the thermal history of the universe, here I took this view graph from an old paper by Bagel, which is who he is or was, maybe he was, a specialist of galaxy evolution, also cosmology. He did a lot of things, as many of the astrophysicists back in the 1950s. And here you have the time after the Big Bang. So do not pay attention to the linear scale. It's not linear at all, as you may see. 10 to the minus 42nd. This is the Planck era. So the Planck era is the time at which we are able to start counting time, as you know, because of the Heisenberg principle. We are not able to go past this barrier and to measure times before. So there's no before, but here we start counting the time, and it's 10 to the minus 40 seconds. The inflation that I talked about, which is something that was added to the first Big Bang model, happens very quickly here, and you see that in these very early days, you are able to build the first forces, fundamental forces, the electroweak, and you build quarks also, and the nucleosynthesis. So the moment when you have all the building blocks for matter only happens 1 second after the Big Bang, after we start the clock. And so 1 second after the Big Bang, the temperature is of about 10 billion Kelvin, so very high. And at such temperatures, deuterium nuclei can be formed by a combination of a proton and a neutron, because here we are already in the phase where quarks combined together into protons and neutrons. But it cannot survive, because the energy of the medium is larger than the binding energy of the deuterium. So you form it and you destroy it, you form it and you destroy it, and you can note it as this. You have kind of an equilibrium. Proton and neutrons give birth to deuterium and a photon, which the deuterium immediately is split into proton and neutrons. And this goes on for 2 seconds. And in these 2 seconds, the temperature, as you see here, has dropped quite dramatically, 1 order of magnitude in 2 seconds, which is quite a lot, because the universe is expanding very fast. And then, as you go to 1 billion K, which is, you remember, the temperature that I talked about to overcome to have a classical nuclear reaction. So if you want to build hydrogen without having to build deuterium without having to tunnel, okay, without tunneling. This happened in the early universe. And then the synthesis of deuterium becomes efficient, meaning that when you build a deuterium, it's not split again, because the binding energy of the medium is, the binding energy of deuterium is now higher than the energy available in the medium. And so this is the starting point of the Big Bang nucleosynthesis. So the Big Bang nucleosynthesis is building protons and putting a proton and a neutron together to build the isotopes of hydrogen. Other reactions, so you are here, you have a neutron that is put together with a proton. First you have neutrons. Neutrons, they have this beta decay that I talked about earlier, so beta plus decay. And so they decay, emitting electrons and antineutrinos, and you start to have protons. Once you have these protons, they are still embedded in a soup of neutrons. They are also capable of capturing neutrons, which makes deuterium. This deuterium is now embedded in a soup where there's deuterium, but also protons and neutrons. And so there are several pathways for it to evolve. The deuterium can capture a proton, which will yield helium-3 and a gamma and a photon. It can also capture another deuterium atom, and this will lead to tritium or to helium-3, depending on what particle is emitted also with the daughter. So either it's a neutron or a proton. So you build up helium-3 and tritium, and again, capturing deuterium particles will yield helium-4. And this helium-4 will be captured on helium-3, which will make beryllium-7, which is unstable. It will decay into it will capture a neutron and go into lithium-7, and the lithium-7 will capture a proton and go back to helium-4. So what you see is that you build hydrogen. These are the main products, the different isotopes of hydrogen. And you also build essentially helium-4, because the other forms that you build, in particular helium-3, is destroyed by deuterium capture to make helium-4. So these are the main products of the Big Bang nucleosynthesis. And so this is important, because if we look at this, we only have a solution for how we build the X and Y blocks that I talked about on the astrophysical periodic table, you know, and we don't have the Z. And so now you understand why we don't have the Z. Actually, very new computations show that you have tiny bits of lithium, just 10 orders of magnitude less than the other ones. And you have even tinier bits of carbon, some isotopes of carbon, that can also be built in these conditions. These are the latest results. But still, it's 20 or 30 orders of magnitude less than hydrogen and helium. So that's why we say that Big Bang nucleosynthesis is all about the X and Y. So what's the problem of this Big Bang nucleosynthesis? It's exactly that it stops at helium, essentially, and you don't build something else. So why does it stop at helium, and why is it the main product? It's the main product because, according to everything I said earlier this morning and what we know about nuclei, its binding energy, you see it here, is the largest among the lightest elements. The light elements which are here, everything that is lighter than carbon, helium is by far the most bound. And also, as you see, it's in a peak, so it's not the higher because it's in a monotically. Okay, well, it's increasing just in a row, but it also decreases again before it increases. So it's also the nuclei around, which are lithium and helium-3 and hydrogen. They have lower binding energy, meaning that it's easier for them to capture particles and make helium-4. So helium-4 will be the end product of this nucleosynthesis. The other point, which was a problem for a while until the 50s, and we will come to it later, is that when you go to the nuclear chart here that I put, so here it's the bottom of the nuclear chart, you have all the isotopes of hydrogen, helium, lithium, beryllium, boron, and carbon. And if you go to the value of stability here, you see that you have stable isotopes with mass atomic number 1, 2, 3, 4, but there's nothing at 5. The lithium-5 is unstable. It doesn't remain. And again, you have something at 6, but nothing at 8. So you have here kind of nuclear barriers that yield the following thing, is that if you have processes that build up nuclei with atomic masses 5 and 8, they won't stay here. So you have kind of a barrier. If you cannot go past 8, how can you go to the heavy elements? That's the problem, okay? Because nothing is stable here. So, and we will come to it later, and it's stellar nucleosynthesis that can explain this and how we build these ones, despite the fact that there's a huge barrier here that explains that during the Big Bang there was no heavier element built. And so this, I will just finish on the Big Bang nucleosynthesis. So the heavier elements are also produced, but in small amounts, due to their higher Coulomb barrier. So here are some view graphs. There are lots of curves. Do not worry if you can't read everything, but as you see, there are some carbon here and nitrogen. So here are all the isotopes of carbon and nitrogen that can be produced according to models of Big Bang nucleosynthesis in a few minutes. You see here the time in terms of seconds, but here you have the mass fraction of these elements, and you see that it's lower. It's 10 to the minus 15 to 10 to the minus 30. So there are really more than traces, and they are included, but in fact they do not really play a big role. The ones that the main outcomes of Big Bang nucleosynthesis are hydrogen here in red, and its isotopes, the deuterium and tritium, and helium, helium-3 and helium-4, and some traces of the lithium ones. And you see that everything happens within some minutes, because you have this peak, and then, as you see, all the curves get flat. And why do they get flat? It's because now the universe has cooled down a lot, and you do not have stable elements, heavier elements. So it's very difficult to overcome the Coulomb barriers. And the density has dropped a lot also, and so nothing moves anymore. And so you have to wait for stars to happen to go beyond this. So we will finish with this and have a small break. So this is the result of Big Bang nucleosynthesis, and so this is the validation of the Big Bang nucleosynthesis, or the way the Big Bang nucleosynthesis validates the Big Bang model. So what you see here in these plots, what is shown is the number of baryons per photon, which is called eta in cosmology. So it's a fraction of a number of baryons, depending on the number of functions. And the baryonic density of the universe, which is here noted omega beta H2, which corresponds to 10 to the 7, something like this, of this eta value. This value can be measured with studying the fluctuations of the cosmic microwave background, which was done by the Planck satellite, and you get this value. So this is the density of baryons and of the universe as constrained by the best measurements that we have, which is Planck. And now you also have the results of Big Bang nucleosynthesis computations, which are the blue lines here for helium-4, deuterium, helium-3, and lithium. And in green, these are measurements. So how do you measure primordial abundances? Since we are in our neighborhood, we don't have primordial matter anymore. But we can go to high redshift galaxies. We can also spot in high redshift galaxies some gas content. And we can have an estimate of these abundances in some very old stars also. And what you see is that there's a concordance. Everything coincides, everything just crosses at the same point for helium-4, for deuterium, for helium-3, not for lithium. So there's a small problem with lithium. But if you forget about lithium, because lithium you build very few, this is very important for stellar people, but for the matter people, what you see is that, great, the Big Bang works. We predicted something and everything aligns. So this is a validation of the Big Bang. For lithium, it's been a problem for a long time, and I think it's a more or less solved problem, because lithium can be either built but destroyed, but also built in stars. And so the lithium, the problem is that it's not primordial anymore. Lithium has been contaminated with stellar evolution and with cosmic ray spallation, which is very rapid neutrons and particles bombarding heavy seeds and making lithium, beryllium, and boron in the proportions that we observe now. Because if we would look at only Big Bang nucleosynthesis, we would have much less lithium, beryllium, and boron than what we observe in the cosmic abundances. And to understand this, it was the work of Hubert Reeves, before being known as the classical astrophysicist with a white beard and a Canadian accent. He is the father, he is the one with Jean Audouze, who understood what was the lithium, beryllium, and boron nucleosynthesis through this spallation, cosmic ray spallation, in the early 1973, the paper. So this is not an issue, and now you know the first boxes of our periodic table, where they come from. They come from Big Bang, and it seems to hold.